What up, dudes? We're going to start up our chemistry class today, and here's my video recording for you. I've got some students that are cutting out things on the packet, and so what I'll probably end up doing is like pausing and starting this recording. Lab today for chemistry. I appreciate people coming in from like EA. I appreciate everyone coming in, particularly if you're coming in from like way far out there. And I know that anyone who's watching this and is from the mainland, like Pittsburgh, is thinking, man, you guys are all wimps. That's not that far at all. An hour drive? Are you kidding me? That's what we do when we go to the grocery store, right? Probably.
Everything is really close.
Yeah. Okay. What kind of lab can I come up with for teaching the periodic table? Because I think that I've decided that I decided to push Chapter 3 back a whole week, right, to give us some more breathing room to cover topics. And so this is kind of me helping out with nomenclature and periodic table because this is my way of slowing things down. So could I do a lab where we got to mix some cool chemicals and watch things explode?
Yes, you could.
No, but I can't with the periodic table unless I had magnesium or sodium and that kind of stuff. And I don't think we have that in our budget right now. I'll try to get some though, because I think it would be really cool. I'll show you some videos. So what I decided to do was I wanted to show you the rhyme and reason behind the periodic table. I think that was really important to me. It's important for me to show you that at least. All right? So today's lab is actually going to be a lot of arts and crafts stuff, but I think it's going to be a good one. And I worked really hard because, see all of these Pokemon cards? I actually created each of them in Adobe Illustrator. And created all of these different things for you guys by hand. It sucked, but it took me like all night. And I'm all tired and grouchy and, yeah, appreciate me. All right. So, I want to show you a video. Let's see. Mendeleev. That's a good one. Full screen. Can we screen? Where's the full? There we go. Enter full screen. There we go. All right. So let's do this. You guys see? You guys won't be able to hear it because just listen to what I'm saying. Please watch the video because it took me a long time to kind of come or use these animations and whatnot. All right, so imagine you're in Siberia. See, Siberia. And you have a blind father. And your 13-year-old boy and your blind father just died. Too bad because you've got 10 brothers and sisters. But to make things work for you, your mom opens up a glass factory, and hopefully she wants to send you to school one day. But 1 year later, the glass factory burns down. Bummer. Your mom sees you as having the ability to be this great scientist, this amazing scientist. So she ditches your brothers and sisters. Seriously, I really don't know what she did with them. And she puts you on a horse, and she travels 1,200 miles to the University of Moscow. And she begs for you, please let me in. And they reject you. So then she goes and travels another 400 miles to the St. Petersburg, where your father has graduated and actually used to teach there. And with that good old brewski, we can do it attitude, they accept you. And there's a picture of a butt there because your butt is sore from being on the horse for that long. That would be 1,600 miles. You have completed your mom, having completed her mission. Didn't show a picture of the mom dying?
Yeah.
She died after she did that. That's my story of Mendeleev. Thank you very much. Go home. No, I'm kidding. That would be... Did you like that animation?
Yeah.
All right.
It looked like, what's it called?
Crash course.
Yeah, I actually stole that part from Crash Course, cut out the audio, and just did the audio myself. Because I wanted to tell different things or specific things about it, and I actually think Hank Green is really funny, and so I sometimes grab stuff from him, but I like customizing all of my own things. That would be plagiarism, by the way. Don't turn in that kind of work for me. I'm allowed to teach it to you that way. All right, check this out. I can add and take away electrons. And if I do, what happens? It changes what? It changes positive. What do you mean? It becomes an ion. That's the word. It becomes an ion. And an ion can be either positive or negative. Cool? All right. And this, I showed you this picture already in the last lecture. And you just be like, I'm hit. I lost an electron. And you'd be like, are you sure? I'm positive. Tough crowd today. Tough crowd. Okay. You can also mess with the number of neutrons. For example, we have hydrogen with 1 proton. We have hydrogen with a proton and neutron. And we have a hydrogen with a proton and 2 neutrons. And those are called, do you remember? Isotopes. There we go. Awesome. Your brains are on. So that would be messing with the number of neutrons. And when you mess with the number of neutrons, what does that change? The mass. The mass of it. Exactly. All right. Look at calcium. Okay. Find in your little packet, you have calcium. In this little packet, right? No, in the Pokemon card one with the shells. Find calcium on there. Okay. Calcium, how many electrons are in the first shell of calcium? Can I see your calcium real quick? Calcium. Alright, I already drew this for you, so this will be. Alright. Calcium is that. Let's draw it up on the board. So, here's calcium. As you can see it right here. Calcium has how many people in the how many electrons in the first shell when we draw it? 2. In the next shell up, how many does it have? 8. We can't fit any more inside of this shell, so when we can't fit any more, we add to the next shell over here, and that would be how many? Another 8, and then over here can hold
2.
Yeah. Well, I mean, over here there's only 2, but it could hold, yeah, that kind of stuff. Actually, I think, if I recall, because it's been like 10 years since I took chemistry, when you get into the upper shells over here, these shells kind of mix in, and there's some shells that can hold like 16, I think. Or was it like, yeah, there was like 2, 8, 8, and then something else, I forgot. 10, that was it, right? Anyway, all right. We aren't really going to get into that range right here, but I need to introduce to you this concept of a valence electron. So what happens is when a shell gets full, it kind of shields the outside. It kind of shields what's outside of that shell to the effects of the nucleus. This thing has 8 in it, and so it kind of like shields this thing over here, and you have these 2 extra electrons on the outside. Celeste, feel free to stop me if I'm speaking baloney, because I'm approaching this from a physicist's point of view. It kind of shields this thing. So what happens is we have this thing called valence electrons, and valence electrons basically mean the electrons that are outside of the full shell. So in this case, calcium has how many valence electrons? Don't all answer at once. Yes? Yeah, exactly. It has 2. Does that make sense? Because the outermost shell has 2 extra in there. And even though calcium has 1, 2, 3, or this is 8, 16, 17, 18, 19, 20, even though calcium has 20 electrons in there, the first 18 are all inside of these nice little full shells. And so the extra that we have left over is 1 and 2. Cool? So here's what I want you to do. I want you to go through these cards right here. And I gave you a spot to put how many shells you have. So calcium has how many shells? How many circles do you see? 4. How many valence electrons does calcium have? 2. Awesome. So I want you to go through every single one of these cards, and I want you to write in the number of valence electrons and the number of shells. Do that now, please. I'm going to pause the camera. All right, so just a real quick heads up. What we're trying to do today is we're going to actually try to be Mendeleev, and we are going to. What I want you to understand is the thing that pisses me off about science is this idea that I have called the black box theory, and I feel like a lot of times students think that there's like technology is inside this black box that they can never understand, like a calculator. You can't understand how a calculator does what it does. You just know that you plug in the things and out pops your answer. And what I always love to do is strip away all that technology and explain the essence of what's going on. To me, that's really important. Why make you use a calculator when I can teach you how to build the calculator? You see what I mean? And then you folks are thinking, well, we'll never have to build a calculator in this world. And I'd be like, well, if you folks want to be the pioneers of this world, then you need to understand the intricacies of how things work and why they worked and why they came about, not just using them like blind people or whatever. So what I wanted to do was I wanted to make sure that you understood that this periodic table wasn't this thing that we found in the middle of the desert, chiseled onto a tablet, and we pulled it out of the sand and we said, ha, look, the periodic table. I wanted you to see that it actually comes from a logical way of putting things together. Do you understand? My biggest pet peeve for those of you in my math class, and I'll say this, and I've actually, I don't know, maybe this is inappropriate, but my biggest pet peeve is I always hate when teachers pull things out of their butt and throw it off the board and say, memorize it for the rest of your life. What I like doing is I like explaining where it comes from, how it got there. I can't stand when teachers just pull the equation, like the quadratic equation, saying, look, negative b plus or minus the square root of b squared minus 4ac all over 2a. Memorize that. Where'd you get that from? Just do it. I want you to understand where it comes from, how we got there, that it's not magic. And so that's kind of what I'm doing with this lesson. So here's what you got to do. All right? I want you to organize this period or these elements. And what I want you to do is I think that I'm going to ask that you lay them out on your table and work with your partner. So both of you folks use one set. Okay? And I want you to put all of the elements that have the same number of valence electrons together. And I want you to arrange it vertically. So the same number of valence electrons. Actually, you know what? Let's do that first. I want you to group them all in different piles according to how many valence electrons they have. Cool?
So we only need to share one packet.
Yeah. Oh, but I want you to make your own packet so you can do this at home as well. So you don't waste your time. Why are you looking at me all pissed off?
Because this is really tedious.
Dude, how do you think Mendeleev felt when he didn't even know what was going on?
I don't know, but I feel bad for that dude.
Alright. So, did you guys separate them into all, packets that have valence electrons? You guys didn't even start. It's just like thinking Mr. Dalton's gonna talk. Impress you.
Oh, okay.
I mean, come on, this is at least a lab.
Okay.
All right. Okay, pay attention to these instructions. After you group them with the same number of valence electrons, what I want you to do is I want you to put them in order as far as the least number of shells to the most number of shells. All right, I'm going to walk around and see how you folks did. What did you create? I know. I'm just asking you because I started recording. This is the rhyme and reason behind the periodic table. This is the important part to me as to explain where we got it and why it comes about. And to be honest with you, this is not what Mendeleev did. Mendeleev, I think what he did was he arranged it according to the mass of the elements, or maybe the density of the elements, or something like that. And his periodic table was a little bit inaccurate. It was close to this, but it was a little bit. He had things switched around a little bit. And then, but at the time, he didn't even know about electrons and valence electrons and all of this shell theory and that kind of stuff. So he did pretty good to kind of start us off on this process. So anyway, that was Mendeleev, and that was creating the periodic table. I think that's really important. Take those cards and kind of put them on the side because I don't want to mix up all these cards that we have out. Now, next thing, I want to talk to you folks a little bit about the different parts of the periodic table. Let's see. So this is what you created. I actually had to go into Adobe Illustrator and make each dot and then place them all. It's a nightmare. All right. We call the vertical parts groups. And as you can see, those vertical groups have the same number of what? The vertical groups have the same number of what? Maybe I shouldn't have had you put them away, but these vertical groups all have the same number of valence electrons. And the horizontal rows, those all have the same number of shells. Very good. Because of that, they have these certain properties. For example, let's talk about the alkali metals. Those are the first ones. If you look, the ones that have one valence electrons, those folks are very reactive. Why are they very reactive? Well, because they want badly to get rid of their electrons. So they're going to react with anything that will allow them to get rid of their electron. So they end up being very explosive, very reactive. Here's a good video clip that I like using. Let's see. I wonder if I can... All right. This is a balloon filled with hydrogen. I actually did this experiment. I cannot do this inside of the school here. Manning Tate tried to blow up a small little bottle of water, and he almost got arrested. So, okay, check this out. I know! That's crazy! I know, I really want to. I was thinking that, and I'll definitely get arrested.
Hasn't Miss Solanini done some experiments?
I was thinking, oh, we can go over to the park over there and blow up a hydrogen balloon. Yeah, right outside of the Senate. That would not.
It sends the right message.
That would not bode well for Mr. Dalton. I'll tell you that much.
We all have a good laugh.
yeah. Right before I get arrested. It would. That thing, like I've seen this thing, hydrogen balloons blow up, and that thing shakes you to the core. Did you guys have like really bad thunder yesterday?
Yeah.
Like it's that loud. It's almost like boom. And whoa. And I think the crazy thing is the Germans kind of came up with this idea one time to be like, well, hydrogen's lighter than air. You know what we should do, you guys? You know what we should do? We should make a blip out of hydrogen.
Ah, the Hindenburg.
It's called the Hindenburg. It did that. A lot of people died. I'm not really. I mean, it's not like a look how funny it is, but I mean, that you can see how that's a bad idea.
That was German karma.
Was that?
I thought it was pretty funny.
Yeah, it's kind of, I guess, maybe one of those things where like you can laugh about it now, but then there was, if you really think about it, it's like, wow, a lot of people died of that. It's kind
Yeah,
of more.
but they were German.
Yeah, ooh, ooh,
Millions of lives.
ooh.
I'm German too.
You know what you should do? You know what you should do? You should backpedal. That's what I learned how to do after I got married. Hey, let's check this out. I actually like this video right here. So I wish I could bring some of this stuff into the class and show you. And maybe I might be able to acquire some. So I'll see if I can. Here's potassium. This is the stuff that's in your bananas. Potassium?
How do we not explode?
Yeah. It's the diluted nature of it. I mean, you don't really need that much potassium. But if you had pure potassium, it's actually, it almost looks like a rock that's almost like chalky, kind of. It's very malleable. You can kind of squeeze it and it has soft. You take it and you throw it inside of water, and it wants to react so bad. Why? Because that one valence electron is like the freaking extra electron that I got on the outside. I want to get rid of it so bad that I'm going to react with anything I can. You throw it in water, boom, the thing explodes. Here's another one. I think this is cesium. Look at cesium on your periodic table. How many valence electrons are we dealing with? How many? Cesium. All right. How many valence electrons? Look on your periodic table. Say it out loud, please. One. Because it has one.
Cesium under oil. We now need to lift it up using the new device and then drop it in the water. And let's see what sort of chemical reaction it does today. Everybody ready? Neil?
It's pretty cool, huh? All right. That would be cesium. And that reacts really well with things because we have an alkali earth metal. All right. Trends in the periodic table? Okay. Let's take a look at the valence electron 0. Which column would that be? Or not column, but where is that? On the right-hand side. Now, the right-hand side is a really interesting side. Because it has 0 valence electrons, are they super reactive?
I don't think so, no.
Why not?
They don't get rid of anything, nor do they need to gain anything.
Because they're happy. Because they're like, dude. In fact, they're all like, they're so high maka that they're like, I don't want to interact with anybody, right? In fact, we call them. This is how I remember them. They're the noble gases. They're the noble gases. They're so like. I don't want to even interact with you. I don't want to react or interact. I'm all by myself. And the noble gases don't react with anything, and it makes sense as to why they do, because they have 0 valence electrons, so therefore don't need to react with anything. Let me watch this video real quick. I feel like I'm going to run out of time, and we might not even get to the Pokemon thing. Darn, what happened? My YouTube thing messed up. All right, here. Let's look at YouTube. Let's look up noble gases. Balloons. Take a look at this one, because I like this one. I think this is cool.
Here are 5 of the 6 noble gases.
It's only like a minute long.
Neon, argon, krypton, and xenon. They're all colorless.
Look
and
at your
transparent.
thing and make sure.
Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. gases get denser. Helium is lighter than air. Neon is just lighter.
That's pretty cool, right?
Argon
It just floats up just a little bit.
and krypton, I've just got to unstick these from the anchorage for a moment.
Yes, and it is called krypton.
Argon and krypton are both heavier than air. And xenon,
Listen very carefully. Wait for it.
xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
Huh.
I know.
It's that heavy?
Yes.
Oh my god.
It's a balloon filled with air, and it just goes boom, and it just bounces like I don't even think it bounces. It bounces like a medicine ball. Like it doesn't bounce at all. It just drops to the ground. All right, hey, dude, this is my class. Oh, sulfur hexafluoride. This one's actually pretty cool. Maybe I'll let you watch this one.
Alright, so here's what's happening. There's a gas inside.
We'll go ask. We'll talk to Neil Patrick Harris about it. He's Doogie Howser. I don't think you know who Doogie Howser is. Okay, so the different gases. You've heard of helium, and what do you do with helium? Yeah, that's yeah, exactly. Most people would say you fill up a balloon, right? And then I would say no, really. What do you do with helium? And right, it's just like me asking, how do you eat a gummy bear? There is a right way to eat a gummy bear, and you all do it. I know you do it. All right. Anyway,
Oh, I was thinking of another
helium.
activity.
You suck it up, and it goes hey, and you sound all high like Alvin and the Chipmunks, right? There's another gas that you can actually
Make your voice deeper.
suck in, and it's sulfur hexafluoride. The word hexa might mean, like, let's kind of think of how hexa would be 6, so maybe this is, fluoride would be the element, what? What's the
Fluorine?
fluorine, which would be an F, right? So sulfur hexafluoride would probably, have F6 in there somewhere. Yeah, anyway, so it'd be probably like SF6, maybe. I'm just trying to kind of bring this back to nomenclature. Anyway, it's like helium's evil twin, and I think that the...
And let us chat.
Can we get some of that stuff?
I know.
Get some of that and helium and just like.
You know what? If I ever enter a wrestling match, I'd be like, wait 1 second. Sup, dudes? Or something like that. It would be so cool. All right. I really, you know what? I think I need to finish my lecture pretty quickly. I had so many more things planned for you, and I feel like I'm running out of time because I want to get to this one thing that we're doing. Look, here's something I want to do, and I'll tell you what. I want to do our lab, and I want to have a chance to describe it. So I'm going to record this really quick because I do want you guys to see this, and I actually had to run back home to grab my trombone and then run back and try to catch the bus. And so I want to show you this thing as well. So I'm going to start you off on the lab, and then 10 minutes before we have to leave, I'm going to show you the trombone thing because I think it's a really cool idea, concept. You want to see it now? Okay.
You could have built up on it now.
All right, fine. I'll start the recording now. Let's do it. There's this thing that we have to do, and this concept is actually, to be honest with you, it's a concept that I think is really interesting, and I don't even know if anyone has done any research on it. After playing trombone for like 10 years or something like that, I sat down and I'm studying physics, and I realized that there's this thing that happens with my trombone that I was like, oh, that's really interesting. And I think it's a really cool idea. And I'd be interested in talking to another scientist and seeing if this, how this happens. Anyway, trombone. This is a trombone. How do I make the notes change? Yeah, this is known as a thingy, and you pull it. And so I can go a scale and do do, re, mi, and I go. things, and that's actually not the lowest note I can play. The lowest note I can play, or at least try to play, I used to be able to do really well at this. It's been like 5 years since I've played trombone, but is the low B flat, which is. So that's a low. Oh, got it? Does anyone, you play piano, right? Or used to? Do you know bass clef?
Wait, I didn't play a lot.
Oh, you didn't play a lot? Does anyone know bass clef? How to read bass clef music? Kind of, not really? Iffy. Alright. It's been a long time. For me, bass clef, the B flat is way down here. Got it? I think it's B flat. Anyway, I keep looking to you because you're like my chemistry guru, and you're probably like, I've had chemistry recently, but I don't even know. You probably don't know music either, huh?
Yeah.
All right. Here's something interesting: is the next note that I can play is an F. So if I played B flat, the next note would be a C. Got it? But what I'm asking myself is, if I had my slide lock on, that means I can't move the slide. It's stuck. What notes can I play? So I know I can play the B flat. I can play the low B flat. That would be way down here somewhere. I think. I don't know. I don't ever see music that low. I don't play the tuba. The next note up I can play is F. So that would be up here. Okay? The next note up I can play is a tuning B flat. This is the B flat that I started off with. Here's the higher B flat. Do you guys hear that? It's an octave up, or it goes do, do. Okay? There we go. And then after that, I can play a D, I believe. The D is right here. So this is. So here's the notes. And then after that, I think that's right here. I'm not very good anymore. That's too high. After that, it's a higher B flat. And it's like right over here. Now you guys are thinking, what the hell is he doing? He's just playing trombone and he's like speaking a bunch of like notes. Why is he doing it? What are you noticing?
It gets smaller.
It gets smaller. The space in between gets smaller. Here's another interesting thing. This is the medium D. Okay? I asked myself, can I play a D at first position with the slide lock on? All right, that sucked. It sounded like I just picked up the trombone. And what's happening is I'm trying to hold the instrument and make it resonate at a place where it doesn't like being. It's not supposed to be able to hold that note, D. And if I wanted a D, I would move my slide out to here and make the D sound. But instead, either I slide up to an F or I slide down to a. So like I'm trying to play this note right here, and it goes but it doesn't give me the D. Does that make sense? I realized that this is actually the picture of electron shells. This picture has the shells. Imagine that's a big circle. Those shells are right there. And there's a reason, and the shells actually do get closer and closer together. That was a really interesting concept. And I realized that this because I was studying chemistry and playing trombone at the same time. Another thing I realized is that an electron that likes to hang out here, actually it doesn't like to hang out here, never likes to. Because what I was thinking is, why do electrons hang out in shells? Why is there only a certain area that they like being in? Does that make sense? Why doesn't it like being, why can't it be anywhere? As long as it's within the, within a, here's the nucleus. Why can't it be like here and halfway in between here and a third of the way in between here? Why does it have to be set here, 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 here? And I realized that's the same idea behind what I'm doing with my trombone. And when I have an electron that's in between, what it does is it naturally slips up or it slips down, depending on if the shell is full. Does that make sense? I thought this was a crazy concept. And here's the really crazy thing, is if I were really good at playing the trumpet or the trombone or the trumpet, and the same idea goes for the trumpet. You just have to say, how many notes can I play without touching the valves? Because you go do-do-do-do-do-do-do. When you get up high enough, and when you play trumpet high enough, or trombone high enough, you can actually play any note. At the super high octave, it's like 3 octaves above what I can play. And you can play any note without moving your slide at all. It's so high that I guess the trombone just resonates all at that energy level. And that would be like bringing an electron way up to this high energy level. And that's actually a really cool concept that scientists are working on, where they can say, well, that would be pretty cool because then we can take electrons and move them through shells. Just slip them up and down states pretty quickly, which I don't know if it's possible yet. I haven't kept up. I know that 10 years ago when I was studying this, it wasn't possible. Anyway, that's my trombone demonstration. I thought it was really interesting. I hope that you folks did too. Can I move on to the next part? You guys like that? Thanks. Okay. So here's what I want you to do. What I want to do is, I want to explore the periodic trends that happen. And I'm going to ask you to make a 3-dimensional periodic table. And the way we're going to do that is, let me take a look. Did it just flash?
Yeah.
Okay. Is this your packet? Oh, here we go. This page right here. You're given straws. Everyone needs a ruler. Everyone needs scissors. Everyone needs a calculator. I'm sure that you have calculators on your phone. The ruler, I'll try and get you some. We only have like 20 minutes to do this, so please do this quickly, even if we even have that. I think we have 15 minutes to do this, so do this as quick as possible because I do want people to have this. What you need to do is I want one group to do the atomic radius. I want one group to do the electronegativity. I want one group to do the ionization energy. So here, you're in charge of atomic radius. You're in charge of electronegativity. You're in charge of ionization energy. You'll be in charge of density of each element. Okay? You'll be in charge of, let's put you on ionization energy as well. Okay? It's not to say I think you'll do a junk job. I'm just saying. Okay. Doubling it up there. All right. Now here's what you do. You've got straws. You need to cut these straws in exactly half. So fold them in half and cut them in half. You might want to take a ruler and cut them in half. These are your new straws. Let me see. All right. All of them. All 36 of them, so you have 72 straws. Then what you're going to do is I want to see if there's certain trends that have to do with the periodic table. And what I'm going to ask you to do is, like, turn to where it says atomic radius. Okay? Disregard everything in the last two rows of the main part of the periodic table. So, like, see this picture right here? Right here? Can you guys see this one right here? Heads up. Do you guys see this one right here? All right. Scratch out the bottom four rows, because I only want you to build it up to rubidium, all the way down to rubidium. Got it? All right. Here's what I want you to do. What is the biggest number that you see in the atomic radius? Huh? No, what's the biggest number? It ranges between 31 and 270. What's the biggest number you see? No, I see a 248. Remember, I asked you to cross out the bottom four rows. Here. I'm going to ask everybody to do this. I'm going to ask everybody to build the periodic table, which looks something like this. I only want you to build hydrogen, lithium, natrium, potassium, and rubidium. We're gonna stop after this row. We're gonna scratch out these bottom ones. You guys are gonna be here all day cutting straws if I made you do the entire periodic table. In this thing, what's the biggest number you see for atomic radius? Look at the paper. What's the biggest number you see? I'm trying to help you out here. 2 what? 248. 248. So here's what you do. I want you to now have your straws, which are all the same size. The longest one is 248. So how tall is this? Say this is 6 inches, or I don't know. This is like 4 inches, or 10 centimeters, or something like that. I don't know. 10 centimeters equals 248 for the number. And then what I want you to do is I want you to scale each of these. So the next one down is 215. So 10 centimeters equals 248. Then how many centimeters is 215? Do you guys know how to solve this thing? If 10 centimeters equals 248, how many centimeters is 215? I'll show you, it's really easy. Yeah, you just divide. 10 over question mark, or how's about this? Question mark over 10 is equal to 215 over 248. Got it? And then you multiply by 10. And that's how long you need to cut this straw. So this straw will be whatever this number is. And then you cut that down. You guys understanding what I'm getting at here? So what you're going to do is you're going to have a bunch of straws that are at different heights. And what I want you to do is, like, this straw represents rubidium. I want you to glue it on the rubidium over here. And the next straw, which is for strontium, I want you to glue that straw, or not glue, but tape that straw on that, but you need to cut it down to a certain height. Does that make sense? So what you need to do is you need to find the biggest number in your category. So I think your category was atomic radii. Your category was electronegativity. Both of you had ionization energy, and you had density. I think for you, you're going to have to look up that information. I'm sorry. You might be able to find that information online on a table, because I have the other tables printed. All right? Go. I'll walk around to answer questions.